This video looks at conditional probabilities, so let me set the stage for you. So recently I went to a college training day, and to encourage us to stay for the entire day, we were given a raffle ticket when we arrived, but prizes were not awarded until the afternoon. Very clever. So tickets had two colors. I got a blue one, and I honestly don't know how many people were there for the day, but just to keep it simple, let's say there were 500. I think that's a pretty good estimate. All right. So when they draw the first prize, my probability of winning would be 1 out of 500 until they announced that the ticket was orange, and now my chance of winning became 0. So do you see what happened? The sample space changed. When they announced the ticket color, I no longer had a chance of winning. So let's look at this a little closer. So conditional probability, which we read probability of A given B, is the probability of A and B divided by the probability of B, or kind of easier, the number of times A and B occur over the number of times B occurs. Big thing here to notice is the denominator is just the number of elements in B. So we're not using the whole sample space anymore. Anytime I see the word given or I see that line to say conditional, I change the denominator. That's the big clue of what's going on here. All right, so let's go back to a spinner. We've used this a bunch of times. And notice in this one, if I just want to know the probability of 2, it's 1 out of 6. But I'm going to do the probability of 2 under some conditions. So the first condition is the number is even. So say like we spin the spinner and somebody, and I'm betting on 2, but they're telling me, hey, it's even. I go, oh, my probability just went up, right? Because now there's only 3 even numbers and it goes in the denominator. Or what if I'm looking for the probability of 2 and I know the outcome came out to be less than 5? So there are 4 numbers less than 5, so I have a 1 out of 4 chance of getting a 2. Or what if I get super lucky and I find out the probability is of the condition of the outcome is I know it's yellow, then I know 100% I got the right thing because there's only one yellow slice and it has a number 2 on it. So each time the denominator changed to match the condition I gave you. The condition even, 3 of them, so I put it in the bottom. Less than 5, 4 of them, I put in the bottom. Yellow, 1 of them, I put in the bottom. All right, so why don't you try this one? I gave you 5 things to do. Look at them, try them, pause the video, come back, and let's see how you did. All right, so let's start with the first one. Probability of getting a 5 is 1 out of 6. Probability of getting a 5, if I know the number is odd, now I'm bumped up to 1 over 3. Probability of getting a 5 if I know the outcome is not red. So I have 5 other things, 1, 2, 3, 4, 5, that are not red, so I have 1/5 chance of getting a 5. Probability of getting a 5 if I know the outcome is greater than 3. So I have 3 numbers, 4, 5, and 6 greater than 3, so my chance becomes 1 out of 3. The probability of getting a 5 given the outcome is less than 2 is 0. If the outcome is less than 2, no way is it a 5. So there's one way to get something less than 2, but 0 of those things are a 5. All right, let's roll a pair of dice. And this time I want to find the probability the sum of the dice is a 4, given I know that I got doubles. Okay, so let's look at doubles. Doubles are the same number on both ones. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. One of them, 2 and 2, adds up to 4. So one of the 6 possibilities works. All right. Stay with this idea of rolling 2 dice, and this time let's find the probability the sum is at least 10, given I rolled doubles. So again, the denominator stays the same at 6. I have 6 doubles, but the ways that it could be at least 10 would be 5, 5, or 6, 6. So I have 2 of my outcomes are at least 10 out of the 6 outcomes I could get all together, so I have 1 out of 3. All right, so let's look at some sports. So here, in the regular 2015 season, the Denver Broncos won 12 games and lost 4. That means the probability of winning was 12 out of 16, or 75%, and the probability of losing was 25%. But let's take a little bit closer look. So here's a chart of their wins and losses based on where they played, if they were at home in Denver or if they were away. Then I can see a little bit something different happened. And let's look at the conditional probability really to feel what happened. So the probability that they won, given that they were home, I had 7 wins out of the 8 home games. So that's 7 over 8, or 87.5%. The probability they won when they were away Well, they won 5 of their away games out of their 8 total away games, which is 62.5%. So definitely a difference there between winning at home or away, which means there's also a difference where they lost. So lost at home, they only lost 1 home game. So that's a 1 over 8 or 12.5% chance of losing. But away, they lost 3. So 3 out of 8 is 37.5%. So do you see this home field advantage here? The Broncos won more at home and they lost more away. That is what conditional probability is when some condition makes an outcome more or less likely to occur. So we specified a certain aspect and we got a different result. This happens sometimes, but not always. And what I mean by not always is, look at this example. Let's check out the Bucks. All right, so here come our Bucks. So in the regular 2015 season, the Tampa Bay Bucks won 6 games. They lost 10. That means their probability of winning was 37.5%, and their probability of losing was a whopping 62.5%. And like we did for the Broncos, let's do the same thing for the Bucks, and let's look at home versus away. And let's do the conditional probabilities of each. So look at home. They won 3 out of the 8, which is 37.5. When they were away, they won 3 out of the 8. Again, 37.5. Exactly the same. Lost home, 5 out of 8, 62.5. Lost away, 5 out of 8, the same, 62.5%. The Bucks had the same result both home and away. All we can say is they're consistent, but for the Bucks, the condition of where they were had no effect on how they played. They won and lost at the same time. So I just want you to know that even though conditions can make a difference, they can also not make a difference. It just depends on what we're actually looking at. All right, so let's look at some other examples. All right, so this is Chicago shootings. I got this idea from watching the presidential debates. They've talked a lot about Chicago, and I thought, hey, I'd really like to know what's going on there. So I went around the internet, found a bunch of sites, but this was the best one I could find, so I borrowed this from them. This is a site called Hey Jackass, and it's actually a really interesting site. They do a great job of just showing you all the different statistics, and they keep it up to date, so you can see this is January through October, and the shootings that have happened so far. And again, if you want to check it out, there's a lot more there than I just pulled one little section of it. So here, these yellows represent fatalities, so people that were killed, and these represent people that were just wounded. So I need to add them all up to get the total number of shootings so far, which gave me 3,560. Really a scary statistic. And then the total fatal shootings, I add the 51 and 55, which gives me 606. Just so we can wrap our heads around the numbers better, I put it into a chart. All right. So we're going to go through and do a bunch of different things to see what happens here. And I also want to show you how to take words and turn them into something much smaller, because students tell me they have a hard time with word problems. So I want to reduce the words and get right to a problem as soon as I can. So the first one, find the probability a person was shot. A person shot was killed. So I'm just going to call that probability killed. Find the probability a person was killed given. So let's take a pen out and underline this given being important. They were female. So we're still doing probability of killed, but I have a line given female. Same thing happens here. Find the probability a person was killed given they were a male. So killed given male. And then I flip it around. Find the probability a victim was female given, there we go, they were killed. And then probability the victim was a male given they were killed. So I did kind of a forward and backwards because I want you to see that order matters. So just like, sometimes we're looking at when does order matter in math, when does order not matter. I want you to see that with probability. So let's work through these. Okay, so just probability someone is killed in general. I take the total people that were killed, 606, over the total number of people that were shot, 3,560, and it says 17%. Then I look probability killed, they were given they were a female. So 51 female that were killed out of 368 that were shot, says 13.9%. Killed given a male, so 555 killed out of 3,192, so 17.4% of men that were shot were actually killed. Then I flipped it the other way. Female given this person was killed, so I had 55 females that were killed out of 606 fatalities, which is 8.4. And then a much bigger number of the shootings, 555 were men out of 606 shootings in total, which is 91.6% of fatalities were men. These are numbers to really think about because they're not made up. Just like the Bucks and the Denver Broncos weren't made up, these aren't either, and this should, just show you, things to think about, things to be concerned about. All right, then I said, well, let's look at, it doesn't matter where you get shot because this whole picture shows different places. So if you, what's the probability you got killed if you got shot in the arm? Really small. Only 6 people died from being shot in the arm out of 524 that were shot in the arm, which says 1.1%. So you're not very likely to die from an arm wound. But if you get shot in the head, that's much more scary. So the people that were killed from being shot in the head were 238 out of 475 people that were shot in the head. It says you got a 50% chance of dying if you get shot in the head. Pretty scary. All right, so let's go lighter. Let's go to Facebook. All right, so I made this survey. It's fake, but I did get it off of real ideas. I looked at percentages of people, so it is the right kinds of numbers, but instead of giving percents, I just gave you numbers. So I want you to try this one. See if you can answer these 4 questions. Pause the video and then come back and let's check out the answers together. And for simplicity, I made up these little things that I decided FB would be Facebook, not FB. I put a little slash, M is male, and F is female. So let's use that, and here's the notation I came up with. So the first one, probability a person on Facebook given they're female, FB given F. There were 75 women on Facebook out of the 100 women, which says 77%. Find the probability a person is female given they are on Facebook. So that same 77 women, but the total people on Facebook was 143. So it says 53.8%. So a little bit more women than men on Facebook. All right, then I flipped it. Find the probability a person is male given they are not on Facebook. So male, not on Facebook. So he's male, not on Facebook, 34. And then the total people not on Facebook, 57, which says 59.6% of people not on Facebook are men. And then find the probability a person is not on Facebook given they're a man. So I go back to men, not on Facebook, but then the second part is a male, so I divide by 100, which says 34%.